Hi everybody, welcome back. Today we're going to start looking at epidemic models, how to model epidemic propagation. So I've got a little video animation here of what kind of model we're going to use, which is going to be a model of an agent-based type. So what do we mean by that? We have these two people, one in red and one in blue, walking around, and each of them has a territory that they live inside, and they're actually walking at random, and then at some point they meet, and when they meet is the moment at which one of them who's infected, this red one, might be able to transmit an infection to the blue one. So there are various types of epidemic models. This is just one possible type. It's, as I said, an agent-based or individual-based model where we're actually trying to track individual people. And so that's the model we're going to look at for the next couple of lectures. So in order to implement that on a computer, we need to be able, for example, to say, how do these walkers move around in space? So they're going to take random jumps and choosing a random direction to jump in. And then we have to say, how do they actually transmit the disease? Well, that might happen with a probability of infection as well. So how can we model probabilities in the computer? So we're not really assuming that you know much about probability. We're going to sort of develop the intuition using computational tools, as is the theme of this course. So we've already used this function called rand in Julia. Rand, because of, stands for random. And so, for example, if I have a vector of friends written as strings, I can choose a random friend to call, for example. And I just do that by calling this rand function on this container object. The container has various objects inside, and it's just going to pick a random one. And we saw that in one of the videos this week as well. So for example, if I just keep running this function, we see that I'm choosing a different friend each time. Sometimes I repeat the same friend, and then sometimes I don't. And because we're using Julia, we can actually use this function rand with objects of many different types. So currently there's something like 80 different methods of the rand function without importing any more packages. So for example, I could take a random element of a tuple as well. And if I do that, I see 1, then 2, then 1, etc. So it's a pretty versatile function, but what is the point of this rand function is to choose one of these elements in this collection in a way that you would call at random. I'm going to choose an element at random. What do we actually mean by that? We mean uniform. And uniform is a technical term that means that I'm going to choose each of these elements with equal probability or equal chance. And the actual act of choosing an element is called sampling. So I'm doing random sampling of these objects in the vector and in a uniform way, so the probability of each of them occurring is the same. But what do I really mean by that probability of each of them occurring? Well, one of the ways that we could think about that, not the only way, is that if I do this sampling many, many times, we expect that the frequency of each of these outcomes, for example, the frequency at which I will choose to call Alicia, is approximately 1/4 of the time because there are 4 elements in my vector. So basically, if I have n elements, I will choose each one with a probability 1/n. That means that in the long run, if I sample millions of times, I expect to see that approximately 1 million divided by n of those times I get Alicia. But I also don't expect it to be exactly equal to 1 million divided by n. And we'll see that later on in a computational way. So let's use this, for example, to roll a die, a classic experiment in probability, and we can easily do that on the computer. So let's take a die with 6 sides. By the way, die is the singular of dice. Dice is the plural of die. So I'm rolling 1 die for the moment. So let's take 6 sides, and then this sides object is 1 to sides. That is a range, right? We know that is the type of that object is actually a Julia range object. So it represents this vector from 1 to 6, but it does not actually store the values in memory. But there's this again, I can specialize the rand function on this kind of object, and it will just choose one of these numbers between 1 and 6 uniformly. So again, I'm sampling uniformly from that range now, and it's choosing one of these numbers at random, which is like rolling a single die. So we can also repeat this sampling n times by just adding another argument to the rand function. This works in general with a rand function with any kind of object. So I'm now sampling 10 of these and rolling the die 10 times effectively, right? And again, every time I do the experiment, I'll get a different result for this vector. So what would we like to know? Well, if we just look at these numbers, you can see that, oh, well, the number 2 came up 4 times, the number 5 came up twice, and each of the other numbers turned out to come up once, I believe, if I've got that right. So we actually want to count those frequencies. The frequency is the number of times that these outcomes are occurring. I want to count those frequencies. So I'm going to use a function called countMap in the stats base package. So base here refers to the fact that this is a sort of fundamental package for many statistics packages in the Julia ecosystem. Stats here refers to statistics. And countMap is literally going to count how many times each of these inputs occurs. And it will return a dictionary, as you can see here, which tells me, oh, 4 occurred once, 2 occurred 4 times, etc. So exercise, think about how you could write this function. How could we actually write this function to do this counting? Maybe that will be on the homework. Okay, so once we've got the frequencies by using this count map, we now want to plot them, of course. Right? But we don't just want to be staring at these tables of numbers, let's just plot them using the plots.jl package. So there's actually this bar function which draws a bar chart. So this is what's called a bar chart. It has bars and it has gaps between the bars. This is because this data is discrete data, right? I have, just the values 1, 2, 3, 4, 5, and 6. I don't have any intermediate values. Later on, we'll see a similar graph, similar looking graph that means something a bit different, which is a histogram. Okay, so we're seeing the outcome and we're seeing how many times that outcome occurred. For example, 2 occurred 4 times in this particular experiment. Let's run it again and we can see, each time we run it, we get a different result. For example, you could say, well, how likely is it that I get 4 of the same number occurring? So you can see that, well, I had a few tries where I didn't get 4. Here, I didn't even get 3 of the same number. I got, 2 of the same number several times. And here I actually got 5. So for example, you can ask the question, how often will I see 5 of one particular outcome occurring? And that's actually a kind of tricky calculation if you use mathematics, if you do mathematical calculations with probability theory. But computationally, it's pretty easy to do by doing a Monte Carlo simulation. So what we're doing here is called Monte Carlo simulation. That means we're just running a simulation many times with random numbers inside the simulation somehow. So Monte Carlo is a city in the country Monaco in the south, located in the south of France, where there are many casinos and hence many random numbers are being generated by physical means. So by the way, I should just say that computers cannot actually generate true randomness. You can get true randomness by recording atmospheric noise or a noise from an electronic circuit, and there are actually websites that will give you true random numbers, but it's useful to be able to generate pseudo random numbers or random things that look like random numbers in the computer, and that's what this rand function is actually doing. We won't go into the details today. Maybe there'll be a video on that next time. Okay, so now I said that this sampling was uniform, that we're expecting to get an equal number or approximately equal number of 1s, 2s, 3s, 4s, and 5s, and 6s. And if you look at this graph, you'll see that that's just not true at all. It's very, very far from being uniform, which would be flat on this graph. So what's going on? So, what we're going to do is just increase the number of rolls that we're doing. And maybe as we take more and more rolls, it will become more uniform, and that's actually what happens. So what we're going to look at is now the relative frequency or proportion of the roles that come out to be 3. So I'm going to divide the outcome, the number of roles, I'm going to divide that by the total number of roles. And now I'm going to, so we're going to start off with just 1 role, and then 2 roles, 3 roles, etc. And as I add more and more data, you can see how this bar chart or bar graph changes. So we're looking again at the relative frequencies or proportions. What is the proportion of 3s out of the 66 roles that I have, and how does that compare to what I expect to find, which is that they're all equally likely, which would be with probability 1/6 for each of the 6 options, which is this horizontal red line. And so you can see that as I add more and more data, well, it still doesn't look very uniform, but I can increase by a lot the amount of data. Actually, I could even go up higher, let's say 10,000 roles, and see what the data does. And okay, yeah, it does actually seem to be getting much closer to uniform. It's still not quite uniform, but we could, for example, say, well, how far away from uniform are we? And we could try and work out a way to measure that. And then you can actually prove, using advanced probability theory, that as you take more and more roles, the probability that you will be far away from uniform goes to 0 in some particular way. And that's called the law of large numbers. Okay. Oh, by the way, how did I do a simulation? I actually pre-generated the data. Because we're using random numbers, it doesn't make sense that every time I move the slider, I just completely regenerate a new set of data. What I want to do is generate the data once and for all. That's what I'm doing here. I'm restricting to a total maximum number of roles, and then I'm generating that number of random roles at once. And then this histogram, this bar chart, is just taking the first 97 in this case of that data and doing the bar chart of those 97 elements. So when I add the next one, it's still taking the same data up to 97, and it's just adding a new datum at the end. And that's a general thing that we should always be doing when we're running these simulations with randomness, to make sure that it makes more sense sort of intuitively to us. Okay, so what are we actually doing? If we think about this mathematically, what we're doing is we're generating this outcome. So let's call the outcome something. We'll call it capital X. But every time we run the experiment, capital X is actually changing in its value. And so capital X is an example of the object that we call a random variable, a type of object that we call a random variable. So it's actually pretty difficult to define a random variable. You need to take a probability course to do that. We'll just have this intuitive idea that it's an outcome that is random, but it has a limited set of possible values. For example, here it can only take the values between 1 and 6 in this particular case. And what we're interested in is, what is the probability, what is the frequency or chance of this value being, for example, equal to 1? And so we're going to write that as blackboard bold P of x equals 1. The probability that x takes the value 1, what is that probability? Theoretically, it's 1/6. In this particular simulation, in this particular example, it's about 1/10. That's called the empirical probability. Okay, so now, what could we do with this? So suppose we want to infect somebody with probability 1/6, right? When these two individuals meet, with probability 1/6, we do transmit the infection. So how could we do that? We could actually roll a die, and if the die came out to be 1, then we would do the infection. Otherwise, we would not. So, okay, that's okay if we have a probability of the form 1 divided by something. But what if we had, some real number and we wanted to generate an event with that probability? So what we could do is use real floating point random numbers. So if we do rand of float 64, it will actually generate a random number that's uniformly distributed between 0 and 1, and is a real number now. And we can actually leave out the float 64 and it will do exactly the same thing, because this is sort of the most basic random number generation you can do on a computer in a way. And so so Julia provides that function with no arguments. Okay, so let's actually visualize this, and we're going to take some number of samples, and then again I'm pre-generating the data. So I'm taking 500 samples just 500 random numbers between 0 and 1 uniformly distributed, and we're going to plot them. So let's start out. Here's my first random number. It happens to be around 0.35, and so I'm just plotting on the x-axis where these random numbers appear, and on the y-axis I'm going to plot the same random number in the same position on the x-axis, and I'll just plot on the y-axis which step it appeared in, sort of some kind of time as I'm generating these random numbers. Just it helps the visualization. So let's start generating these numbers, and you can see that on the x-axis they spread out in some way along the line, but they leave these gaps sometimes, right? And as I add more data, I expect that those gaps will be filled in. If they're not filled in, then I certainly am not generating numbers in a uniform way. But you can see that, for example, up to now, you might suspect that doesn't look uniform because there's this gap there. But as I take more and more data, eventually those will be filled in. So this is actually what randomness looks like. It actually has more clumps in than you expect. So for example, if you look at this data in 2 dimensions, you can see there are these sort of big spaces. I just happened not to get the right data in the right part at the right time, and so you get these clumps. Anyway, but as you see, what I'm doing is filling in this, so these are the random numbers I'm looking at on the x-axis, and they're filling in the whole interval from 0 to 1 in an approximately uniform way. And so how could I use that to now generate an event with a certain probability p? Well, first of all, let's plot a histogram of this data. So that's a similar plot to what we had before, but now we're going to actually split the interval 0 to 1 into boxes and count how many of these numbers fall into each box. Why do I need to do that? Because these numbers can actually fall anywhere on the line, so it doesn't make sense to say what is the probability that you fall exactly at a particular value. That probability is actually 0. So let's do that with these histograms. So I'm going to fix the number of bins to be 10 to start with, and I'm going to start adding data. And as I add data, you can see that I have these 10 bins of width 0.1 each, and I'm counting the number of data points that fall into that bin. Again, I'm pre-allocating the data. So as I add more and more data, we would again expect that we think we're doing uniform sampling. We think that the result should be flat. We think there should be exactly the same number. We think in our heads that intuitively there should be the same number of points in the interval 0 to 0.1 as the interval 0.1 to 0.2, but actually there aren't. And so let me take some more bins, and you can see that really it's quite far from uniform. But then I can actually increase the number of samples again, let's say to 10,000, and then as I take more and more samples, it gets closer and closer to uniform, meaning that the distance away of each value from the mean value that I didn't actually draw should be getting less and less. Okay, so that's uniform random numbers. Now let's use those to sample events with a given probability, and this is called a Bernoulli trial. So let's do the same visualization again, and now I'm going to add my random numbers. Here they are. So let me put that slider down again, the maximum number of samples down to 500 again, so we can get a bit of a better view. And so here we go. Here are my random numbers. And now what I'm going to do is say I want something with probability less than 1/3, say, or less than 0.31. So I'm going to put my slider at 0.31. There it is. And now what I'm going to do is say that, oh look, if I take these points which fell less than, whose x-coordinate is less than this value of p, then actually the proportion of those compared to the total is approximately p. So that's what I'm going to use, right? So as I change p, I'm picking more and more of the points with a higher or lower probability as I change p, these points that I've highlighted here. And so the algorithm is actually quite simple. I'm going to generate a uniform random number, also called uniform random variate. That's the outcome of a random variable, is called a variate, using rand, and then I'm just going to check, is that number less than p? If it is, I'll return true, otherwise I'll return false. And Julia has a simple way to write this in this nice syntax, Bernoulli of p, which is like, I'm going to define a function using this short form function definition, equals, I'm going to take my random number and compare it. Is it less than p? So remember that comparisons in Julia have a value. For example, 3, is 3 bigger than 4? It is not. If I change it to 3 less than 4, it returns true. So that is actually, you might think that you could write that as function, Bernoulli 2 of p, if rand is less than p, return true, else return false. And you can certainly write it like that, and it will do exactly the same thing, but there's no point in doing this because this expression already has the value that I'm returning. So I can just write it like that. Okay, so what is this Bernoulli random variable? Well, it is a random variable actually. The outcome of this, so I can think of this as flipping a coin, but the coin is biased. It either falls on heads with probability p or tails with probability 1 minus p. And so all the possible values, all the possible outcomes are just 1 or 0, true or false. And I know their probabilities. I want probability p for having heads and probability 1 minus p for having tails. This is called the probability distribution of my random variable, when I specify all of the possible values and their probabilities. So now let's flip many coins which are biased. So how could I do that? So I want to flip 10 coins. I can use an array comprehension for that, and I call the Bernoulli function that I just wrote. So if I do that, I see every time I run the function, I get a different set of 10 values, trues and falses, and I should get true approximately 1/3 of the time, or 3/10 of the time. So let's define a function flips of np to do n coin flips with probability p. So I can take this array comprehension and just run it through the function called count, which literally counts how many true values there are in that collection. But it turns out that I actually don't need to put these brackets in. If I don't put the brackets in, I now have a different type of object. It's no longer an array, it's called a generator expression. And it looks like this. And so that is something that does not store its results in memory. An array always allocates memory and stores the results there. And a generator expression does not. It just generates a new value each time you ask it for the next value. And count does not actually require you to store anything in memory. And so it's more efficient to use this option. So I timed it, and it's something like, you should time it too using benchmark tools. It's something like almost twice as fast in this particular case as using an array comprehension. Okay, so now what do we want to do? We want to, so this is going to, this flips function is returning me a number, the number of coins that came out to be heads. In this case, it was 7. Let's run it a few more times. Okay, I got a 10 there, and there's a 4 sometimes, etc. But what I never am going to see is 0. It's very unlikely to see 0 come out. It's very unlikely to see 20. So actually what I want to calculate is what is the probability distribution of the result of this calculation. So this is a new random variable. Every time I run the calculation, I get a different answer, and I want to know what is its probability distribution. And so I can run the experiment with this new function, run experiment n and p and a number of times, and it's just going to collect the data from running this flips experiment a certain number of times. And so we can then look at the probability distribution in exactly the same way, and it looks like this. So as I add more and more data, you can see that, oh, well, actually, around 30, sorry, I'm running with 100, let's run with 20 instead, 20 coins. Then, so I'm going to add data, and it's going to concentrate somewhere around 6. So it turns out that 6 is, the most likely probability in this particular experiment, and then it's very unlikely to see a number of heads that's bigger than, say, 11 and smaller than 2. But as I add more and more data, it will gradually, it will manage to spread out. And you can see that when I take a very large number of experiments, basically this picture stays the same. So what's happening is that what I'm calculating is the distribution of this data set that I'm sampling, and that's called the empirical distribution. But as I take more and more samples, here I've taken 1 million, it actually converges to a shape, and that shape is called the population distribution, which is the underlying theoretical distribution of this random variable, which is the number of heads in 20 coin flips. And to finish, let's change this 20 to something bigger, say 100, and do the same experiment again. So here we go, I'm going to add more and more data, And as I add the data, it concentrates in a similar way to the way it did with 20. But now when I take a lot of data, we see a very familiar shape, which is this bell curve called the Gaussian distribution or normal distribution. And so this is an illustration of the famous central limit theorem that what we're actually doing is we have the result of a coin flip is a random variable with the value 0 or 1, and we're actually summing up n of those random variables. And when we sum up n independent random variables, they usually converge. The result, the distribution of the result usually converges to a normal distribution in a limit. But to make that precise, again, we need an advanced probability.